next talk of Graham White from Southampton that will talk about why quantum gravity made me fall in love with domain walls.
So obviously thanks for that introduction. Thanks for the to the organizers and for the lovely invitation. So obviously the title implies that there was one time where I wasn't a fan of domain walls. I spent a lot of my career and continue to do so working on other gravitational wave sources, such as strings and phase transitions and scalar-induced gravitational waves. But recently, I've been more convinced that domain walls are a much more likely source of primordial gravitational waves. And in this talk, I want to go through the reasons why. So first, what are domain walls? So they appear when you have a discrete symmetry in your potential. So simplest example, just consider this standard Mexican hat potential. And there's two minima with the same value. A positive VEV and a negative VEV. And the potential has the same energy at both VEV, so there's no reason for the universe to prefer one or the other. And this seems like a little bit of overkill, but it becomes a more useful way of thinking when you think of more complicated topological defects. But you can kind of think of the manifold as a the vacuum manifold as a very, very simple manifold. It's just a discrete it's just a disconnected manifold made up of two points, which I've labeled by this X here. So the solution to the equations of motions you can get when you solve the Euler-Lagrange equations. And you have the usual boring solution, which is so you have the VEV at plus or minus this value here, the square root of mu squared over 2 lambda. But you also have a more interesting solution, where you have a kink which varies continuously from one vacuum to another. So this V equals mu over square root of 2 lambda times a tanh. It has the prefactor, which is your VEV, and then you have a tanh function which goes from one VEV to the other. So this we can show explicitly as a solution to the equations of motion. What we do is we plug into the Euler-Lagrange equations, and we just immediately show that three of these derivatives will vanish. So there's no time dependence for this solution. It's just depend on Z. And so therefore there's also no X or Y dependence. And so your Lagrange equations just has this second derivative of this tanh solution with respect to Z equals the potential differentiated with respect to the VEV, plug in the Z. And so subbing in a tanh solution on both sides, we find indeed we have something which looks like a sesh times a tanh. And then when we plug this into our Lagrangian, what we get is we get a localized energy distribution. So this plot on the bottom right, so the yellow curve is the value of your VEV. It goes continuously from one VEV to the other. And so you have this, and then you have this clump in the middle, that's your energy as a function of Z. And so it peaks very narrowly with a width. And so this is why we call it domain wall, because it's basically just this wall in space, wall of energy in space. So how do these domain walls scale as we continue just talking about some of the basics of these domain walls? So they scale, so the energy of a single domain wall is just basically the area of the domain wall times the surface tension. Assuming that these domain walls are non-relativistic, these are absolutely huge, so they tend to be quite massive compared to the temperature. And so you have this surface tension, which we denote by sigma, times r squared, which is our radius. We're ignoring all factors of pi or any assumptions about the shape of the domain wall. And so then we could convert this energy of a single domain wall into the energy density domain wall just by taking the number density. If we assume there's roughly 1 per Hubble volume, then what we have is we have, and that these eventually stretch out to be the size of a Hubble volume, then the energy density domain wall will go as r squared over r cubed, which will be 1 over r, which will scale as a to the minus 1. So that's the energy density domain wall is scaling very, very slowly. If you compare to radiation, we expect the early universe to be dominated by radiation. So the energy density should dilute as a to the minus 4. And so this is diluting much slower than radiation. So the fraction of energy density in domain walls will grow as the universe expands. And if we have no way of annihilating these domain walls, then they end up dominating the universe. So about 30 years ago, this was known as a problem. These domain walls, we don't want them in our theory. They appear a lot. They appear in guts. They appear in when you have symmetry breaking chains, you can end up with domain walls in some of your symmetry breaking chains. They also appear in discrete symmetries, which can appear a lot of your model building. You have discrete symmetries. And so this was known as a problem. You see in the 90s, problem, appearing in a lot of titles of papers. These were seen as pesky things. You can get rid of them though. So people thought of ways of solving this problem. And the way you get rid of them, it depends on what sort of domain wall you have. So if you have a local discrete symmetry, you can maybe, if you have strings in your previous symmetry breaking step and they're connected to domain walls, sometimes these domain walls, you can get rid of them by eating them with strings. For global discrete symmetry, you need to find some other way to annihilate them. But for your local ones, there's 2 ways of eliminating them. And so one is you have if your symmetry breaking steps are really, really close together, you can have a you can tunnel these strings, but they have to be quite close together because it's a Schwinger process, which is where the it's a non-perturbative process where the nucleation rate is suppressed exponentially by the ratio of the symmetry breaking scale, so the 6th power. So you need them really close together. So the other step is the domain walls can form as flux tubes in the strings and destroy this string network. For global symmetry, so you could in principle have global strings as well. If those aren't getting destroyed by the time the domain walls appear, then maybe you're in luck. But that means that's not typically, that doesn't sound particularly well motivated. So one option you can have is to have a symmetry breaking term, an explicit symmetry breaking term. And so that will introduce a bias where the universe does actually prefer one over the other. So you produce these domain walls, but one will have slightly less energy over the other, and so there'll be a pressure difference between them, and they'll collide into each other, and they'll collapse. And so that should destroy the domain wall network. And so when people found this out, oh wow, we have some solutions to domain wall problem. Then naturally you think, well, this is such a spectacular process in the early universe, these domain walls growing and then annihilating. Maybe we can actually turn this problem into something really, really nice. We can produce some gravitational waves and have a really nice signal. And so that's very nice. So it turns out that this signal, it comes from actually just like strings, when fluctuations on the world sheet produces gravitons. Fluctuations on the world volume will cause is your source of gravitational waves. So they're basically like, if you ever go to the southern states of the United States, you have these wobble boards. And so basically you have these wobble boards in the early universe, which are producing this this music of gravitational waves, and so this is maybe a way of seeing them. And because they become such a large fraction of the energy density in the early universe, then we expect quite a large signal. So these are hard to simulate, these gravitational waves. It's still a process of simulation, but you can do a bit of physics by tilde to know roughly what your gravitational wave signal is going to look like. You don't have to do the full simulation. And so so basically let's do some scaling relations. So your gravitational wave power spectrum is just a d rho dt, and it's given by your number, and so it scales as your number density of your domain walls times your gravitational power of your gravitational waves from a single domain wall, and it's related to your gravitational wave energy density, gravitational wave abundance, by you just change the frequency domain, so you have to make a change of variables, and you divide by the critical energy density. So let's see how everything in this relationship scales. So we'll start with the power. So the power goes as g, your Newton's gravitational constant, times your energy density times your mass of your domain wall. This is how you can work out fairly simply. This is how the power of your gravitational wave will scale. And so this mass we already discussed is given by the, for non-relativistic domain wall, is given by the surface tension of the domain wall times its area. And so therefore we get the power goes as your radius squared. So then your number density of your domain wall, if we assume that there's a constant amount per Hubble volume, goes as radius to the inverse cubed. And so therefore we can then when we take the power, which is the number density, which is this yellow, goes as r to the minus 3, times the power, which is r squared, we get something which scales as r to the minus 1, which will scale with redshift as a to the minus 1. However, that's the dilution of our source, which is going as a to the minus 1. But then we're producing gravitational waves, and those gravitational waves, once they're produced, that's an energy density, goes a to the minus 4. So overall, we're producing something which goes a to the minus 5. Now we need to divide by radiation domination to give us this green part, which will give us an a to the 4 piece, because it will dilute as a to the minus 4, and it's in the denominator, so we get a to the 4. So the final thing we have to do is we have to multiply by the frequency, and we have to make this use the chain rule in order to change the frequency. So the FTT during radiation domination goes as a to the minus 3. And then our frequency also will give us a factor of a to the minus 1. And so then when we put it together, so the radiation domination goes as a to the 4, because it's inverse. The source will go as a to the minus 5, our frequency a to the minus 1, and then the FTT a to the 3. We get something which scales as f to the minus 1. So as long as these domain walls appear, the wobbles, the signal we'll see today, as you go to the infrared, will grow with f, or as you go to the UV, will go as f to the minus 1. So then eventually they'll annihilate, and they should annihilate very, very quickly. And you can use causality to say that once they annihilate, if they annihilate quickly, the fastest that the infrared part of the spectrum can go is f to the cubed. So you should get a spectrum which goes as f to the cube, some mystery stuff which goes at the top where you have annihilation, and f to the minus 1. And in fact, this is exactly what we find in simulations. So we get a peak which grows as f cubed and will peak roughly near the energy density maximum which we produce, which can be very, very, very large, and then we go as f to the minus 1. So it's a very shallow drop off. So if you have multiple gravitational wave detectors, you should be able to see different parts of the spectrum and confirm that you have f to the -1, and confirm that indeed you're seeing a great domain wall source. So this caused a bit of a different attitude towards domain walls. So for now, if I look at Inspire and if I look at the if I look up the search term domain wall and gravitational waves, we see basically this exponential growth in gravitational wave papers of domain walls. And here are some recent examples. So now it's got a bit more hype. We'll say, wow, this is since we discovered gravitational waves, we're producing all these detectors. This is a signal. So I wasn't too enthusiastic about this particular source, and I want to go into why I didn't like this. And so if you have a look at this bias term, and you ask the question, how big should this bias term be? So you can work out what is the temperature at which these domain walls annihilate, and it'll scale with this surface tension to the -1/2, and it'll scale to the with this bias term, this phi to the 5th over lambda to the power of 1/2. And so we see with this particular bias term we put in, it's natural. We don't have to choose that term. And so we have the surface tension will go roughly as UVev cubed. Your bias will go as UVev to the 5th. And so that means when you plug everything in, your annihilation temperature will go as roughly, there's a factor of 10 to the 9 there. And it'll scale with your UVev divided by your cutoff term. So if you just want to get rid of them, so you want to set your annihilation term to the VeV, then you already have an unnatural scale separation. It's already Planck scale. So all of a sudden you say this is already Planck scale. But if you want to do something fun with domain walls, say produce gravitational waves, or I've seen baryogenesis and other cosmological applications, you need to have them last long enough to contribute non-trivially to the energy density, which means an effective scale beyond the Planck scale. And so this was kind of yuck. So you say, okay, I'm going to, the Planck scale is the highest scale in my theory, and in order to produce these domain walls, and I want them to live long enough to produce a gravitational wave signal, I need to have something above the Planck scale, unless I do some crazy model building in order to avoid that. Okay, so well, we chose our particular bias term as this phi to the 5th term. What if we did some natural other choices of the bias term? We didn't try V contrived, but we did phi cubed. You could do phi cubed, and then you have another scalar theory, which is VH squared, or maybe you have VH to the 4th times phi. And then you find that your annihilation temperature will be the scale that you need to produce is even worse for these other bias terms. I mean, it depends on what this epsilon is, but you end up with something 10 to the 22, 10 to the 27. Yeah, you have something pretty nasty. So if you want to do phenomenology, you want your domain wall, the bias term which you require is yes, just very, very small. So yeah, so this was just not my favorite source. I just thought this was naturally uncontrived. You have this GV, TV scale to the 4th scale potential, and then your bias term is often MEV to the 4th. You just have this really unnatural hierarchy. Now, we have ways of solving hierarchies, of course, but these are ways forced on us by experience. Just having it there contrived, it just did not seem very compelling that you can have this domain wall. However, quantum gravity, it turns out, will actually provide something to the rescue, to provide something. Obviously, something which I didn't like about this is you have something well above the Planck scale, and so it sounds naively that quantum gravity even quantum gravity can't help. But the thing which changed my mind about domain wall was to realize that quantum gravity is naturally giving you stuff which is effectively above the Planck scale. So, okay, so how does this work? So we have this conjecture that quantum gravity is going to spoil any global charge that you have in your theory. Any global symmetry is going to be is not going to be exact because quantum gravity corrections are going to break it, and any global charge is not going to be exactly conserved. So this is so we have these conjectures about quantum gravity, and some of these conjectures are stronger than others. So if you have a conjecture which is purely based on string theory, then maybe if you're a skeptic of string theory, you don't care about this too much. But this one is if it has multiple lines of evidence converging on this conjecture being true, then maybe you find it much more convincing. So what is the evidence that we have for this? The first is we find out that global charges tend to not be conserved if black hole thermodynamics is correct. So this is the idea that you have this thermodynamic interpretation of the fact that your entropy goes as the area. And this can be violated if you're allowed to have at least in the case of continuous global charges. Now that's not discrete global charges, but if but black holes, if knowledge of black hole thermodynamics is correct, this seems to be true in multiple ideas about quantum gravity, not just string theory. Then this is at least for discrete symmetry, you end up with having at least for continuous symmetries that continuous symmetries have to be violated by something to do with quantum gravity. So that's discrete symmetries, but you can then say, well, that's continuous symmetries, but you can ask, why should continuous symmetries be so special? Surely discrete symmetries are going to be the same. And we find out in any known model of quantum gravity that this is the case for both discrete and global symmetries. So empirically, with every compactification of string theory that people have looked at, so this is outside my expertise, so I trust my string collaborators on this. But empirically, we find that it is true that every discrete and global symmetry is broken by quantum gravity effects, either wormholes or by D-branes. And we can also prove this to be true in the quantum gravity theory we understand the most, which is ADS-CFT. So there's multiple lines of evidence converging that this seems to be something true. So it's still a conjecture. You can't prove it as yet because we don't know what quantum gravity is. But it seems to be widely held to be one of the strongest quantum gravity conjectures we have is that global charges are not conserved and global symmetries do not survive quantum gravity. So okay, but that gets you to Planck scale because we expect the quantum gravity to be Planck scale. And so you might naively think this isn't helping too much. So that your symmetry breaking scale should be roughly order Planck scale, which we found out is not high enough in order to do gravitational waves without some tweaking or fine tuning or some sort of level of contrivance. However, at least in the specific cases of string theory, where we understand the theory really well, global symmetry is violated by non-perturbative processes such as wormholes. So since this is non-perturbative, the effective scale of your quantum gravity is suppressed by something above the Planck scale. You get this e to the wormhole action suppression, exponential suppression, which means the effective scale is going to be many, many orders of magnitude above the Planck scale. So if we just plug in what do visible domain walls look like, what the scale of quantum gravity to be. So we just say, okay, we're just going to say that our frequency, we want it to be we want our gravitational wave to be roughly above 10 to the minus 16, because that's our best futuristic detectors, whether that's Theia, DeSigo, or Mu-Eras, the ones allegedly coming on in 2050, if the world's around still then. And we want it to be below the ineffective scale, and we want it to be so we don't want the gravitational waves to be too big, and we want our frequency band to be between 10 to the minus 9 and roughly kilohertz in order to see something. And then if we look at, okay, what is, if our quantum gravity scale is the Planck mass times this exponential, what roughly do we expect the wormhole action to be? Well, if we have the wormhole action be roughly between 23 and 35, that's where we get visible gravitational waves. Now that's really, really interesting, because according to my stringy collaborator, that's a really natural scale. So there is a field where they are trying to like get a particular value of these wormhole actions in stringy compactifications. My collaborator tells me that basically, in order to solve the axion quality problem, you need a wormhole action of 100, which is really hard. You really have to contrive it. You have to really choose a particular compactification to get something that large. It's very unnatural. Whereas 23 to 35, 23 to 35, this is a really natural range, and it's a broad range. So you don't have to try hard, allegedly, to get a action in this range. So if string theory is true, there are you have these zillions of moduli, and it's very, very easy to have these approximate string discrete symmetries appear. So if string theory is true, or perhaps just some sort of other theory of quantum gravity, then there seems to be lots of reasons, very, very easy to get these discrete symmetries, which are approximately broken by something by effective scale well above the Planck scale, and you break them in the early universe because you have these moduli. And so if you ask me, this is at least on par with other gravitational wave sources. So your phase transitions, if you consider, these are, I mean, you just need symmetry breaking in order to have this, and so that's, in some ways, that's much better than domain walls, because you need a discrete symmetry break, you need to last long enough, and you need your scale to be high enough. But phase transitions, they get a penalty in terms of my level of excitement, because you typically need your phase transition to be very strong. It's very easy to break symmetry and have a second order transition. It's very easy to break a symmetry and have a weak transition, which is below what we can detect. Cosmic strings are brilliant. I love cosmic strings. However, there's this a little deeply concerning debate over whether field theoretic treatments are correct of your string network. If these field theoretic treatments are correct, then perhaps you don't have a strong string theory at all. So if you don't know what that is, the idea is that if you model what your gravitational waves look like for a Nambu-Goto string network, then you end up with this nice, beautiful flat spectrum which scales linearly. The abundance of your gravitational waves will scale linearly with your scale of symmetry breaking. So you have this huge range of symmetry breaking scales. You can see very, very nice source. However, if you try and model things from a field theoretic perspective, where your strings are these solutions to the equations of motions, then you have this problem where it likes to decay quickly into very, very quickly into radiation and collapse. The string networks collapse before it gets big enough to produce a large gravitational wave network and act like Nambu-Goto strings and decay predominantly into gravitational waves. So that gives some penalty, the fact that these are beautiful. If that can be resolved positively, then that obviously strings are probably the most exciting and likely source. But you get some penalty from the fact that we don't know if there is a string source. And then the third source is your spontaneously induced gravitational waves. And these are very nice. You just get a period of either ultra slow roll or a period of matter domination, which lasts long enough and then ends abruptly enough. Now, these you get, this is matter domination is easier to produce in the early universe, but the fact that you have to end it abruptly is some penalty. At least some forms of matter domination don't end abruptly enough. And the fact that you need these sources to last the matter domination to last long enough gives it some penalties. So I think like as a source of gravitational waves, these domain walls they're at least as plausible as the other sources, and so they should be taken very very seriously, even though it looks naively like you have this unnatural hierarchy in order to solve the domain wall problem. So if domain walls are something which we should be excited about, what exciting things can we do with them? So obviously with phase transitions, we can do exciting things. We can explain baryon symmetry. We can explain dark matter if we choose to do cogenesis. With strings, we can test leptogenesis. You can be a cosmic witness to the early universe with dark matter. With early matter domination, there's all sorts of things you can do. You could test whether there's primordial black holes in the universe. You could do a nice little test on whether there is Affleck-Dine baryogenesis. And so what can we do with domain walls? Well, there's three things you can do with domain walls. One is you can test quantum gravity, at least qualitatively. Secondly, these can produce your dark matter. And third, they can explain your dark NANO-Grav. So let's start with NANO-Grav. So we've all been very excited about the recent signal. And so you have a look at your domain walls here in this recent new physics fit. And the base factor is excellent. It's like maybe your second most likely after metastable strings. However, your metastable strings for your domain walls is these require a very, very small hierarchy of scales. So that should get you a bit of a penalty in terms of how likely you expect it. So it's very, very plausible source of what explaining NANO-Grav. And so here is a best fit line from our paper about what can explain how you can use domain walls to explain NANO-Grav. For quantum gravity, at least you can qualitatively test quantum gravity. And you might say, okay, a qualitative test, but that's pretty good, right? Because testing anything about that high at quantum gravity, that's not exactly easy, right? And so so this to me is still pretty exciting, even though we're like, obviously we'd all love to know the exact quantum gravity, whether that's string compactification or some other idea. But some qualitative tests is very, very welcome. And so the test is, of course, of the conjecture. So we can so how can we test it? So we're finding domain walls with a bias scale well above the Planck scale. So this could be a really fine-tuned non-quantum gravity bias. That's true. However, at least seems far more plausible if you have a bias so well above the Planck scale that we should believe that this is probably quantum gravity. And we measure the effective scale, and therefore we're measuring a wormhole action. And so this is telling us, okay, that quantum gravity is probably, there is probably some non-perturbative explanation for quantum gravity is probably using something non-perturbative like wormholes in order to break global symmetry. So it's telling us that that is probably true, that intuition we get. And if we can get an independent measure of the effective scale of quantum gravity, then this starts to get a little bit more plausible. So we need observable sensitive to Planck scale physics. So there's a few which candidates. So one is so we have CMB polarization power spectrum can be modified if you have any nonsense being dumped into it at 10 to the 26 seconds. So that's an incredibly long lifetime. And so if your dark matter is protected by this by discrete symmetry, which is 10 to the 26, it has to last for 10 to the 26 seconds, then it's if that global symmetry is being broken, it's going to have to be broken by something potentially well above the Planck scale. Another is neutrinos double beta decay. In some cases, can be sensitive to the effective operators above the Planck scale. And the third is diffuse background and gamma ray observables. So for your CMB power spectrum, so we take the simplest model where we have scalar dark matter. And so then your global symmetry breaking operator is going to give you a mixing term, which is going to be suppressed by your quantum gravity term. And so therefore your decay rate is going to go as 1 over lambda quantum gravity squared. And so so then you have your CMB, but also SKA can also see an even larger range. And so this range goes as 10 to the 30 seconds, which is absolutely incredible for this model. So then it's going to depend.
There are only 5 minutes left.
Yeah, that's fine. I'll finish in 5 minutes. So then when I have a look at my range of my parameter space for your simplest models and what quantum scales you can test. So your gravitational wave detectors, you can see here. And for at least for some values of your self-coupling, you can get into the range where SKA can see something. So you can get 2 different ways of measuring it, and sometimes you can get, if you're lucky, you might be able to get 2 measures of your quantum gravity scale. So next you have your diffuse background. So suppose that your dark matter candidate is a fermion. So I'll just fly through this. So then you have decays of your fermion due to quantum gravity breaking your discrete symmetry, which will give you which will be suppressed by your quantum gravity operator. And so once again, you can see that large parts of the parameter space, you see either detection from SKA, your neutrinos double beta decay, or your CMB, and large parts of that overlap with actually what can be seen at future gravitational wave detectors. So in principle, if we're lucky and we see this dark matter candidate, we could see 2 different measurements of domain wall, of a quantum gravity scale, and that can qualitatively tell us about what gravity is. So the next is in producing dark matter. So when these this is something which might have appeared on the archive today, maybe tomorrow. So one idea is when these domain walls collapse, they can actually be the dark matter candidate themselves. And so here's a parameter space. I'm going to have to fly through this a little bit, but you can produce all the dark matter just by your domain wall network and produce a gravitational wave signal. And this can be produced by essentially just quantum gravity model. Okay, so summary and conclusion. Domain walls, quantum gravity makes domain walls a compelling source of gravitational waves in the early universe. You have a natural explanation for this, for what looks like a fine tuning, this crazy hierarchy of scales where you need this small bias term and Planck suppress operators. And this is because the process relevant to quantum gravity breaking your global symmetries is non-perturbative, and your effective operators are suppressed by a scale well above the Planck scale. You could use quantum gravity, gravitational waves to qualitatively test domain wall quantum gravity. So now it becomes much more compelling if you have a independent measure of your Planck scale. And there are some observables in dark matter scenarios, because your dark matter has to be really, really stable, where you are sensitive to Planck's super Planck scale effective operators. You can cross-check the scale. Now, of course, you can come up with a compactification, where one process violates one discrete symmetry and another violates another. So, of course, if you're unlucky, but you could also be unlucky, and the quantum gravity, what looks like a quantum gravity scale, could just be a fine-tuned scale. So we are relying a little bit on luck, but in principle, but not much luck. This is what seems to be the most likely, most conservative idea, most plausible if we do see the signal. If we do cross-check the scale, we should say, well, we feel pretty confident, not certain, but very confident that this is the scale, and this is how quantum gravity is violating your discrete symmetry. It's doing through these non-perturbative processes. And these domain walls are exciting because they are probably, in my view, maybe the most plausible explanation of NANO-Grav. And these domain walls just by themselves, in some parts of the parameter space, they can provide dark matter, but when they collapse, they can provide primordial black holes. Okay, so that is it. Thank you.
Are there questions from the audience?
So thank you for the nice talk. So could you remind how did you get the lower bound and the upper bound for wormhole action?
Yes, so good question. So this is a this is in P. Oh, sorry, press up too many times. Here we go. Yeah, so what we do is we assume that the bias term, we write all possible operators. So we have Higgs to the 0, Higgs squared, Higgs fourth. So that gives you a VEV to the 5th, VEV cubed, and VEV1, and we assume roughly a common operator. Of course, there can be coefficients in front of these. And so this is just to give a rough scale. And so then what we do is we check the what is our gravitational waves. So we check out what is our peak frequency, what is our peak amplitude. And so then we need to make an estimate of the VEV. And so we've got a scan of the VEV, and we say a sum node between the electroweak scale. We don't really expect it to be lighter than electroweak, really, because we haven't seen anything. And we don't expect it to be larger than Planck scale. And so that gives us a rough scale. We're just going to scan over that scale. And so that scan here gives you the variable domain walls on the left. And what we're going to do is we're going to put some cuts on that. And the cuts are going to be, we want these to be visible. So for them to be visible, we need them to be in a frequency range where your pulsar timing arrays can see. So that gives us the nanohertz lower bound.
Mm-hmm.
And then for the upper bound, we want them to be kilohertz, roughly, or I think 100 hertz here.
I see.
And so then we just look at when is a peak frequency and peak amplitude with this particular bias term and a surface tension, which goes as V cubed. For all possible values of V in here, what is the range of wormhole action we get for quantum gravity effective scale, which goes as the Planck's mass times e to the s wormhole action. So that gives you a wormhole action between 23 and 35.
I see. So when we consider, when we can consider higher frequency gravitational wave observatories, then this condition could be wider.
Yes, that's right.
Okay, I see. That's nice. And I have another question. So when we consider lower dimensional operators like a phi cubic, then with some tiny coupling, tiny coefficient, then it's still like a technically natural, right? So even if we don't consider quantum gravity. So
yeah, so it's technically natural, but it's going to be a tiny coefficient. And so I mean, yeah, so if you have Dirac neutrinos with 10 to the minus 12 or whatever,
yes.
you can say, okay, that's technically natural. Your running's not going to be terrible, but
of course, it's not it
not very
requires some reasoning, of course, yeah.
Yeah. So you want to be able to explain why you have exactly B times v cubed.
I see. Okay.
Yeah.
Thank you very much.
No worries. Thank you for the questions.
Are there other questions?
So when you're showing the order of magnitude estimations and through the scaling arguments deriving the spectrum, could you just tell what is the idea behind having that power going as G times sigma times MW?
Yeah, so this comes from so you get this. I'd recommend a textbook on how to derive the power of gravitational waves. So Valenkad's textbook will give you the basically simple calculations for Nambu-Gotti string, but also for domain walls, just basically fluctuations in the world on the world volume. And yeah, this is the scaling which comes out. It comes out as, yeah, you get a G, you get a surface tension, and you get basically the mass of your domain walls. Something better than referring to a textbook. Yeah, I admit I just come back from holidays. I yeah, I can't remember, but that you can find in the textbook. It just comes from that simple calculation, very analogous to your string theory calculation. I apologize for not more detailed answer, but this just is just treating like basically the domain wall version of the Nambu-Gotti action. You can get this scaling, but yeah, the mass just comes from the action of your. You can just derive that from. Yeah, it's just your just because it's r squared times your sigma.
Yes, yeah, thank you.
No worries.
Other questions? So let's thank Graham again.